Okay, so we are going to continue in chapter 2. So we have finished on on the assembler directives, and next we are going on theoretical aspect. This is nothing of this will be assessed. All these things are not assessed, but this is to help you to plan ahead. But we have done some of this earlier, and as we go on, you will understand what I mean. So the next part is on the program development procedure. So because in chapter 2 we are concerned about writing a program. In chapter 1, we all have written the instruction sequence. But the way how we develop the program and also the way how we actually develop the instruction sequence is almost the same. So what are the steps? The first thing that you need to do, you need to understand the problem definition, or what is the requirement of the question, what the question is asking us to do. Now, based on that, that's what we did with some of the tutorial 2 questions, right? The first thing is we try to define the question. And how did we do that? Can anyone remember how we actually? Yes, we used visual aid. We try to draw to visualize what the question wants. And then what we did, we used some arrows to indicate, is it a data movement, the direction of the movement, or what the question wants us to do. The second thing is algorithm development using pseudocode or flowchart. So do you know what is pseudocode? Well, I'm sure that you have come across this terminology when you are studying C programming. So what is pseudocode? Pseudocode is not a syntax. It's not fully a program code. It's just using a normal English language to describe the flow of the code. So it is much more easier for us to write. Or flowchart. So we either use this, but we didn't use either of this. So what we did, we just draw it, right. Okay, the first step, the first arrow, you move data from here to here. The second arrow, you move from here to here. So we always use that arrow to indicate how we get things moving. So that is also okay. And from that, what we did, we translated, right, from the data movement, we translated into what is the converting the algorithm into assembly language sequence. So that's what we did. We actually convert whatever movements, the diagrams, into possible instruction sequence. We have done that before, right? For example, moving from working register to file register. What are the possible instructions that you can use? Move FF and also move WF. So like that. And then of course you test program using normal data, margin data, erroneous data. And this testing part is where the MPLab comes in. That's where you can actually view the file register, you can actually view the special function register, and you can do the simulation step-by-step debugging, and you can find what each instruction is actually doing. And if you're not getting a result as expected, then you can try to troubleshoot. So is that okay? Any question up to this point? Okay, in C programming, you may have used flowcharts to describe how your program flow is going to go. And this flowchart you will be using until your final year project. A flowchart is an easy way to describe your program flow, what your program will be doing. And this gives, rather than giving the whole code, giving the flowchart is an easier representation of your code. So these are some of the symbols that generally is used. If you see this kind of shape, this is the terminal, start or end. And the square is actually denotes process. Now, what are the things that we actually can include in the process? Defining the variables and things like that. So all that can actually comes under process. And then this is the input or output. So this box you can actually use whenever you're dealing with chapter 7, checking for any input or things like that, or output, sending receiving input or output, but most of the time we use a diamond for input. Why we always use diamond for input is because usually, you see, this kind of input or output, if you in C programming, you'll use the scanf and printf kind of thing, right? But in assembly language programming, and also specifically this microcontroller thing, let's say one of the input devices is using switch. Now in digital hardware, most of the time switches will always give two types of output. All the switches give two types of output. It's either 0 or 1, right? In digital, meaning to say. So because of that, most of the time we always tend to use diamond shape, because it always, is it 0 or 1? So this input or output, well, this in terms of microcontroller that we are using, this is more suitable if you want to display a character in LCD screen, for example. But most of the time input, we tend to use the diamond box, because you want to see whether if the switch is pressed or not. If it's pressed, you do something. If it's not, do something. Because the input switches give us two types of condition. Is that okay? And then you can see this round circle. This is on-page connector. So let's say you don't have to draw lines everywhere, so it looks untidy. So you can have an on-page connector, yes, and automatically you can actually connect here. So this is the on-page connector, and if you have a square box which has double side lines, this main is subroutine. Is not a main program; it's a subroutine. And then, if let's say if you do not have any sufficient page or space, then you can use the off-page connector, whereby in the next page you'll have the same pointing down kind of symbol to denote that this is where the process is being continued. So this flowchart symbols is quite important, but most of the time, especially in this subject, not really is being tested in terms of the flowchart, because we use more of a diagram visualization to make us understand further. But you can see after this, all the examples will use the flowchart to help us to train our mind to think in the proper problem solving method. Any question up to this point? So this is the program start template. By right, you know the part you see this dot 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 and also dot dot dot. You're supposed to have some program code here. You're supposed to have some programming code here. That is when we are dealing with interrupt service routine, which is the topic of chapter 6. But because we are not doing interrupt yet now, for now, so instead of writing program, we are just going to write RETFIE. So you will also learn what is RETFIE stands for later on. But just take note that this part is already reserved. You can see it's high priority interrupt service routine, low priority interrupt service routine. So just for now, you don't need to know what are those. Just take note that those are reserved. So our first line of code starts on which address then? 1A. RETFIE takes 1.8 and 1.9. So it starts from 1A. And of course, here is where you have the main program. Is that clear? Now, have you all tried MPLAB, the code that I've shared and things like that? Okay. So when do you plan? Okay, regarding the case issue, some of you may have encountered some errors, right? For example, when you did the FSR, when you use the LFSR, FSR1, when you write in small capital letter, you get an error. It tells that object is not defined. That is because you need to write the FSR in capital. So whenever you have error, if you have watched the video, in the second video, I would have mentioned that wherever I purposely created an error, right? And whenever there's an error, you just double click on that line and it will point to that line which is error. So then you try to troubleshoot what is the mistake there. Maybe one of the exercises I should give you some wrong codes and ask you to find out what is wrong with it. They have asked that kind of questions before in finals. So MPASM, this is actually the assembler file, allows user to include the .inc file to provide register definitions for the specific processor. As I mentioned earlier, this is the file where it contains all the addresses of the special function registers. All special function registers and bits are defined in uppercase, meaning to say, the F, W, A, banked, all those are supposed to be in capital. But I think it still accepts if you write in small, right? But LFSR, FSR1, FSR0, FSR2, that's supposed to be capital. But when you write in small letter, it throws out an error. So the convention followed in this text is using lowercase for instruction. That means like ADDWF. Convention is it'll use small letter, but if you use capital, it's no harm. And directives, and using uppercase for special function registers. So those are the convention that we follow. And another thing is on the byte order issue. Now this one they have asked before in finals, and this byte order issue is concerning how bytes are stored for multi-byte numbers. So far we have seen single byte numbers, right? Single byte, multiply add with single byte, subtract single byte from single byte. So you have seen that. Now what if you have more than a single byte? How would the arrangements be? So therefore, there are two types of method, Big-Endian and also Little-Endian. So the Big-Endian stores the most significant byte at the lowest address and stores the least significant byte in the highest address. Of course, the Little-Endian, this is like not the Indian song. So Little-Endian method stores the most significant byte of the number at the highest address and stores the least significant byte of the number in the lowest address. Which one of this that you think that we are following or MPLab is following? Okay, let's see an example and let's see if you can get the thing clear or not. Let's say you have a 32-bit number, x 1, 2, 3, 4, 5, 6, 7, 8. How do you know that this is 32? There are 8 digits. Each digit is 4 bits, right? So if you follow the Big-Endian method, so the address and the value, look at the address and value. P, it means the lowest address. P plus 1 means the next address, higher address, and so on. So the Big-Endian method, what it does, at the lowest address, it is storing the most significant byte. 12, then 3, 4, 5, 6, and 7, 8. Little-Endian method, at the lowest address, what it is doing? It is storing 7, 8. And then as the address increase, the next byte. As the address increase, next byte. And the highest address, the most significant byte. So which one are we following? Very good. Little-Endian. So they've asked this question before in finals. So they purposely give a particular number and ask you to solve it using Big-Endian or Little-Endian. So you need to know how those are stored. Is it clear? So we are using Little-Endian, which means the least significant byte is stored at the lowest address. So that makes sense, right? So the least is stored at the smallest address. So why that has to be settled is because after this we are actually going to go through all this more than a single byte addition, subtraction, so on and so forth. So I didn't bring my tablet, so I'm going to attempt to draw on the PowerPoint, which may be ugly. So please take your aspirins if you're going to have headache. So let's say you have one example here. Write a program that adds three numbers stored in data registers hex 20, 30, and 40, and place the sum in data register at hex 50. Now this one is still performing single byte addition. So let's see if I can do this. Pen right. Can I choose the color? So we're going to add three numbers stored in 20, 30, and 40 and place the sum at. So how do you draw this? It's so hard to draw with one hand holding the microphone. Let me just draw this. So this one will be hex. This will be hex 20, right? This will be hex 30. This will be hex 40. And this will be hex 'I don't know why the line kept on coming like this. Anyway, I feel very embarrassed because I'm video recording this. Anyway, so you got the idea? So the content of hex 20 you have to add with the content of hex 30, and you can store the answer here in the hex 30, or you can store in working register. I think storing a working register will be much more easier. And then from here you need to add to hex 40, and you can store the answer in working register. And then you can move WF to hex 50. Is that okay? Are you all here? So here do you see the algorithm, how they actually develop? Okay, first load the number hex 20 in the working register. So what they meant was this one you need to load into. So in our case we try to draw this. So we try to move this to working register, and this one we add with the content of hex 30, and the answer we store back in working register. And then what we do, we add back, and the answer we store in working register. I'm sure you can draw better than this. And finally we move it to hex 50. So we draw like this, and you can actually put the label. This is the first step, this is second, and this is third, and this is fourth. I don't know why it's coming like that, but you all got the point, right? Or maybe I shouldn't record this session. But the idea, so always try to draw in the beginning stage. Of course, you all have been into the subject for quite some time, but practice doing this to get that visual idea. So this is then what we do, you translate each one of those steps. So you can see this is how you write a complete program. So let me get my pointer back. So this is how a complete program should be. So you should have the hash include, the program start template, and then your start and your end. So this is the whole template. And in between, here you should put your instruction sequence, and this makes up a complete assembly language program. So this one, remember the steps that we did. This is step 1, 2, 3, 4. So we translate into each one of that. So we move the content of hex20 to working register, and then you add the content of working register hex30 and store the answer in working register. Then you add the content of working register with hex40, store the answer in working register, and finally you move the content of working register to hex50. That's what we did just now. Is that okay? Any question up to this point? All these things are quite easy, so they can go fast. Can we go move on? Now here's where it comes addition of more than single byte. So write a program to add two 24-bit numbers stored at hex 10 to 12 and hex 30 to 15 and leaves the sum at 20 to 22. Now here is where the little Indian and also the big Indian comes in. So by default, we should use the little Indian method. Let me just draw this. 24-bit means how many, each box that we draw is representing one file register which can store 8-bit, right? So how many boxes do you need? 3. So we have drawn 3 boxes, but you can draw better than this. So we have 2 numbers. So what is the address that you should write here? So this one you should, because of the little Indian, the lower address should be on your most right hand side. So you have hex 10 and hex 11 and hex 12. The bottom number is hex 13, this hex 14 and hex 15. And you need to leave the sum at hex 20, 21 and 22. It's the worst ever drawing, but as far as I got the idea. Now this is because it's the little Indian method. So therefore we have to put the smallest address on the most right hand side. So that the least significant byte is stored here, the middle, and the most significant byte is stored at the highest address. So do you understand the arrangement? So now you need to do the addition. So you need to do one by one. So let's try to so the first thing is you need to add byte by byte. So you need to separate them. So you need to settle byte by byte first. So the first thing is, what do you want to do? So you need to move the first one to working register, and then you add them up And where do you store the answer? So in working register. And finally, from working register, you store at hex 20. So that is you're doing for the first one. Now remember earlier I mentioned that we have 4 addition instruction. Sorry, we have 3 addition instruction. One is add WF, second is add WFC, and the third one is add LW. So we have seen add WF, we have seen add LW, and now, as I mentioned, we're going to see that in chapter 2, and here we are. So when you perform this single byte addition, there is a possibility of having a carry, right? So the carry is need to be added where? To the next number. So when you want to settle the next digit, the same thing applies. What you do with the first one? You move to working register. Now when you want to add working register with the file register, you use add WFC because there's a carry here, right? The content of hex 11 is in working register. The content of file register is in 14. And then there is C. So you use add WFC. And the answer, where do you store? Working register. And from working register, hex 21. I don't know why you always keep it coming out spike like this. Anyway, this look more ugly. No, it's okay. And the same thing applies here as well. The 12 you move to working register, you add WFC because there's a possibility of having a carry here, right? Add WFC, and again the same thing is stored at hex 22. So and therefore you can actually divide this in group. You see the same thing is move WF, add WF, move WF. It's the same thing. The only thing different is this one. For the second byte and the third byte, you need to take into consideration of the carry. Now what if there's no carry? It will just add 0, that's all. If there's carry, then it will add the carry. If you don't have carry, then it will just add 0. But we need to write the code such a way that it will be able to handle the carry. Is that okay? Any question up to this point? Are you able to understand? Sure not? Okay, fine. You all don't like when I say like that, right? Okay, fine. That means something is going to come out. Yes, next week. I hope to get a lot of surprises. Now this one is quite a similar question with a tutorial. Subtract 5 from many locations. It will ask you to teach. Now this is another example. Let me just go out of this. Write a program that subtracts the number stored at 20 to 23 from the number stored at 10 to 13 and leaves the difference at 30 to 33. Now this is a subtraction. But for addition, no issues. You can put arrangement however you want. The subtrahend number can be at the bottom, or you can put it up. Whichever way that you add is not an issue, as long as you follow the proper little Indian way of arranging. But for subtraction, the subtrahend number must be correct, right? Otherwise you might end up minusing the wrong number. So here it says subtract the number stored at 20 to 23 from number stored at 10 to 13. So which one will be up, which one will be bottom? 20 to 23 will be bottom or will be up? Yes, because it says that 20 to 23 from the number stored at 10 to 13. So 10 to 13 will be on top minus the 20 to 23 and leave the difference at 30, 33. So I don't want to draw this. It will end up looking uglier. Oh, never mind, I just draw. So this one is you'll have 4 boxes, right? I don't know why that's coming in. So the top one will be, this will be 10. This will be 11. So I'm just skipping the prefix. Prefix. Sorry, again I'm writing the prefix now. 10 to 13. Then bottom is 20 until 23, and the sum will be at 30 until 33. So the same principle applies here in the sense that you have to do this byte by byte. Now, when you want to subtract this, we will use the sub WF. So sub WF means what? F minus W, right? So out of this, which one should be in working register? The bottom one. So this one you need to be careful. So you need to move the bottom one into working register, and then you perform subtraction, store the answer in working register, and from working register, you can move it to hex 30. Now, if this digit here is insufficient, if it's a smaller number, what happens? There's a tendency of borrowing. So you need to consider borrow at this bit, you need to consider borrow at this bit, and you need to consider borrow, not at this bit, sorry, at this byte. So the subsequent subtraction, when you want to do the same thing, the bottom one you move to working register and you subtract, but you subtract minus with borrow if there is borrow. And then you store the answer in working register and finally move it here. So you can see that here, the subtract with borrow. So you can see in the instruction, the same thing like addition. So all the movements are the same, except that you see the second byte, the third byte, the fourth, all considers subtracting the borrow, if there is borrow. If don't have, then of course it's just minus 0. Is that okay? Any question up to this point? So we will actually end here.